Hello everyone, July 19th. I'm able to do an early, it's actually not that early, it's 12 o'clock, 12:30 right now. But still in the morning, I consider, so let's take a look. Supposedly I think should be easy today. Haven't we done this before? Lowest common ancestor of a binary tree. I think we've done this before. Not too long ago, actually. I think they're recycling questions. Alright, but still, on top of my head, I don't know how to solve it. So I'll probably still have to go through the whole process. So given it's a BST, okay. Find the lowest common ancestor of two given nodes. According to the definition, the lowest common ancestor defined between two nodes until that has both PQI descendants, where we allow a node to be descendant itself. Yeah, I think I've done this before. Like there is a smart way, but I forgot. What's the smart way? I mean, it's a tree, right? So, hold on. Oh man. Yes, I definitely done this before. So we want to find the lowest common ancestor given P is 2 and Q is 8, right? So we say the lowest common ancestor, this and this. So we find the lowest. Isn't like for each one we need to find in its children, see if it exists, right? If 2 is in it and the value are unique, right? If both exist, then this is a common ancestor, but then not necessarily the lowest common ancestor. So if we look to the left, we look to the right, and then we find it, and then that is the lowest common ancestor. If we look, if we look to the left, look to the right, it doesn't exist, but I am myself, then I am not, right? Yeah, I remember I had a solution in the past, but the official one is smarter. I remember it's smarter. I can't remember, man. 2 and 4, yeah, exactly. That's the case. That's the test case. I remember it. Wait, what is the official solution? So 6, right? We look to left and right, and this does not have it, so this is not. So 2, we look to left, does not. Right, we have, and itself. So I say this is the common ancestor. And once we find it, we just return it. Yeah, I think it is, right? So we're given a node. We look to left, we look to right, and we look to the left, we look to right, and if they return a node, not a none, then that is the common ancestor. We return that one. If both return none, then we will. But how do we check if it's in there? Let's see. I remember it's isn't like return Boolean value. +1. If it exists, it's like how many is in there? So we just add them together, right? We return how many we have found. If return value is 2, then yeah, if return value is 1, yeah, so at this position, I check myself, that's get a value, and I check this, will give a value, we check this, will give a value, add it together, if the value is 2, then I am, the root is the LCA, and I return 2. And this one, if the check is 2 already, that means then I don't do anything. That means we already found it, right? We already found it. If the check is not 2, like if these don't give a 2, that means wait, what's the first encounter? First encounter is as we go through a first encounter, once we find it, right? We add it together, it's going to be 2. Then we update it. Then return a value, and the value we check if anyone is a 2, then we don't do. Oh yeah, I think this shall work. Yeah, and I'm pretty sure that is the official solution. I think we solved this maybe like last month. Not 100% sure. Maybe it's last month. They're recycling this and claiming this is an easy question because we have solved it before. Huh. Possible. But doesn't matter. I'm just going to keep solving. Yeah. All right. Oh, that is not what I want. It's not how type hint works these days. This is how type hint works. I think in Python 2, you put a quote on around. All right. We are going to define something called the official def initial. Oh no. Right. Self dot LCA equals none. Right. And then root P and Q. P and Q is no. Okay, so directly equal to no. That's fine. So we say if not root, return none. All right, and then I think we do have to use a. Okay, I think we have to define DFS, right? And every node is going to be a tree node, and P and Q, and this one will return an int, right? This one will return an int, and we say if not node, return 0, right? Otherwise, we say left and right. So left, so overall count, right? So overall count equals DFS node.left plus DFS node.right, right? That's the count. And after the count, we say if count is equal to 2, then just return count, right? Otherwise, if count is not equal to 2, then we say if count is not else, basically just else, then we return, we'll have to set, no. And then we say count plus equal to node equals P, right? Node equal P, or node equals Q, right? So we add that, and we say if count is equal to 2, in that case, self.lca equal to node, and then we return count. Yeah, then we return count, which means actually I don't have to do it here, right? We just say count is this. So if then count is this. If how do I make it? How do I make it? All right, let's do it this way. So self match equals this. So let's do a self check and then count is this plus self match, right? And then we say if count equals to 2 and count equals to 2. No, I don't. Hold up. That doesn't feel right? The count is 1, and the count is 1, and then count is 2. How do we specify that? Oh, we can check on that. Oh, yeah. All right. No. Let's do it easier. So we just say if this plus this, right? If this plus this plus this is, we just say count. Count equals this, right? And then if count is 2 and self.lca is none, then we say self.lca equals no. Otherwise, we return count. Then we do DFS root and return self.lca. Yeah, I think this one shall work. All right, let's take a look. Yeah, let's also include this. I'm not sure, but this one not go wrong. All right, let's try it. Syntax error. Oh, I think I forgot the parentheses itself. 6 and 6. All right, let's do this. Custom test case. Oh, I think it's the same thing. It's 2 and 4. And 4. This one shall return 2. Yeah, and the last one is 2, 1, and 2, 1. So there's 2 nodes. 2, 1, and 2, 1. Let's return 2. Yep. All right, try it. Pending. Judging. Oh, wrong answer. 2, 1, 1, 2. Output no. Expected 2. Wait, what? That is bonkers. How? Ah. What the hell? 2, 1, and 1, 2. That doesn't make any sense. Come on. DFS left, right, and current node equals P or current node equals Q. Yeah. Plus, all right, it's probably because of this. Let's take this away, then try it. Yeah, I think it's this, something is not right there. This one shall be right. Pending. Yeah, this one is right. Yeah, I think what it does is it probably do plus first, plus this, and or this. Yeah, that's not what we want. This is what we want. Everything else is the same. Okay, so I have done this before. Probably in a month, within a month, probably less than a month ago. the solution used here is from either the official solution or someone's solution. It's very simple. We basically check, right? We basically check how many nodes we have found that match either P or Q in the current nodes left and right subtree. And we also check whether the current node is P or Q. Add these values to basically check how many nodes we can find, right, in the current tree that match either P or Q. If the value is 2, that means the current node is a common ancestor. We then check whether LCA has been set before. If not, then the current common ancestor is the LCA. Otherwise, LCA has been found already. And we do nothing. This is going to be ON because each node is visited once. Alright. 92 milliseconds. Ahead of 26. Is it 26, 25? I think that's 26% ranking. Alright. Let's take a look. Problem. Yeah, we've done this before. $235. Let's see. When's the last time we do this? Huh? Hold on. This is not right. It says this is the first time I do this. Wait. I remember distinctively that I have done something similar. Let's see. Similar questions. Which one we did? Lowest common ancestor for binary. Is this the one that we did? Lowest common. Yes, this is the one we done. Yeah, look. This is exactly the same, right? Found left, found right. And this, if added a larger or equal to 2. The lowest common ancestor. Binary tree found the lowest. Oh, because I've done this. This I return count. This one is added together larger or equal to 2. How could it be larger or equal to 2? Then we say res equals node. Realize that LCA satisfies the following condition. LCA equals P, and Q is LCA as a left or right branch. It's Q, P is anything, or the other way around. Yeah, so if not node, we find left from the right, and then we add them together. If it's a larger or equal to 2, then self rests on none. If not, Oh, yeah, if it's larger or equal to 2, I don't know, why would you like, I think it should be like just equal to 2. Huh. Then we do this if it's, but what we use is count. And we return found left or found right or found self. So we return is whether we found 1. So the left branch when you find 1. Right branch, this is better. This is better than this actually. I see the point. I'm now counting, right? So counting is the total number found in left or right, right? And then because of that, we need to check if LCA is none. Right? If LCA is none, that means that's the first time we set. But here we don't have to because we are returning whether we have found 1, right? We don't know whether we found 1. So we can say left branch found 1. It has to be left branch found 1 or right branch found 1, and that's going to be 2, or left branch found. So this is actually, if I do equal, it should be right as well. But the difference is this is a binary tree, a regular binary tree. This is a binary search tree, right? It's binary search tree. So that's why it's faster. We can do something. We can do something to make it faster, I think. Okay, which method do you like better? This is more intuitive to me, right? We just count. How many of those you have found. And this is not how many, but we just say whether we found at least 1. Like if we have 2 on one branch, this one will still found 1. We just say found left is still going to be 1, and found right. Yeah, that's true. If we have 2 already found, that means we have a LCA already. I don't know. Which one you like? Which one you like better? I think this one is count. The other one is at least we found 1. I like count. I like how I do it. So this one is LeetCode 235, which is an easy question. Right, 235. Update. Turns out I have not done this exact problem before. I have, however, done the more generic version of this problem, which is, what's that problem? I have more, 2, 3, 4. So I think I did this before. It's 236. Yeah, I'm going to LeetCode 236. And the solution here is for the generic version. This problem, however, this problem uses a BST, which, well, we shall be able to do it faster, which shall allow us to pick which branch, right, to go to. So we can solve it in log time. All right, so let's just change based on this. So we don't have to do this, right? All we need to do is to check the if p.val is, we need to find p, we need to find q, right? So we say p.val is, I'm looking at myself, right? And then if P dot val is smaller than me, then find P. Find P, find Q. That is interesting. Find P, find Q. Hold up. No, it's find the left. Let's not find P, find Q. It's find the left, find the right. So, which means if P and Q both value is smaller than my node value, then I only need to go node dot left. I don't have to go node dot right, right? And if one is smaller, one is bigger, then we have to go both. You know what? Let's just do this find left, find right thing. Right? But we have to check. We just say if P dot val is smaller than node dot val and Q dot val is smaller than node dot val. If both are smaller, then found left. Yeah, let's go. Found left equals DFS. Yeah, this can be false. Right? DFS. I'm using this one. And found left equals DFS node dot left, and found right equals false. If this thing is larger and this is larger, then we do reverse. DFS right, found right equals this, and found left equals false. Right. Else. Now both need to go. That's my DFS and node dot left. Right. So after this, we say if found left plus found right plus this, right, node equal to 2. I don't think it's going to be larger than 2. If it's equal to 2, then we say self.lca equals node. And we don't need to initialize, because I can just do it here. Oh, not here, but here. Self.lca equals none. And then self.lca equals this, and we're going to return found left or found right or found self. I need to say found self equals this thing, and this is going to be found self. And you have to root and then return this. Also, I am reverting back to the official solution of LeetCode 236 with Boolean return which returns Boolean value. I think you should separate. This is, yeah, let's do another one. I want to keep the previous one. So this shall be solution 2, right? And solution 1 shall be the original. So no, I'm going to put this one here. right? And then this is the solution for this. So I will submit it by itself, and we'll go back here to obtain the original solution, which is fine, very straightforward and simple. Actually, no. We have to only copy and paste this part. But it's slower, right? It's slower than checking the left and right branch, which guarantees us that if a branch does not contain it, then we don't search it. Okay, so let's try this. It returns boolean value. Yeah, it's boolean value. Okay, let's see. Put it here. Try it. Error, syntax error. Oh, why you still have count? I don't understand. I don't need a count anymore. I don't need a count anymore. Name found self is not defined because I spelled it wrong. Found, MD. Found self. Oh my god, I have two. Aye. This one's also wrong. Found self. Alright, let's try it. See if it's faster. I think it should be faster. 80. Slightly faster. So this one give us 80 milliseconds. We'll go to 50%. Alright, anyway. LCA. Let's see. The solution is ON. Oh, it says it's still ON. It's not O-log-N. Huh. But we do this check, right? Huh. Why is it ON? I don't know. For two nodes, PQ, depth of the node. Well, what does N stands for? Number of nodes. We might be visiting all the nodes. How? How will we be visiting all the... Oh, I see. Oh, I see. An unbalanced tree. Ah, yep. That's not right. That's... to pick which branch to go. Yep. And actually, this is more complicated. If you look at this, right, we can just go directly. If it's larger, then it must be in the left or it must be the right. Otherwise, we found a split point. I see. Yeah, this is why it's easier. Got it. For balance is O-log-N. Yeah, that's true. Depending on that. Oh, this is way better. I didn't think about that. Huh? I mean, this is still, I was trying to use the generic version to solve this, but the official solution gives a much better solution. So this is from the official solution, which reveals a very simple fact that in a BST, if p.val and if p.val is smaller than node.val smaller than q.val, then node is automatically the LCA, which we can just say if not node, if not root, return none, right? And then we say if p.val is, yeah, we can do this, right? If both is smaller, but it exists. I don't even have to check for this. It exists. If p.val is smaller, then when we return self.lowest, root.left, p and q, if this, then it's going to be right, and then return root. Oh wow, yeah, that's why it's an easy question. That get blinded, right? Blinded by the official, by the generic version. 4 lines, five lines. Node is not defined because there's no such a thing as a node. Come on, man. There's no node. It's called root because we go directly. No separate function here. This might be faster. It's fewer checks. Yep. It's fewer checks. That's the same. All right, that's it. I didn't realize, right? Because it's binary search tree, so the left and the right, if we split, and that thing is, all right, that's it. That's it for today. I'll see you guys tomorrow. Adios.